Hello everyone, I'm Mahmoud Hamandi and I will be presenting our work entitled A Novel Robust Hexarotor Capable of Static Hovering in Presence of Propeller Failure. During this presentation, I will first introduce the topic of robustness to propeller failure, then I will explain this robustness from a mathematical point of view with emphasis on different Hexarotor designs. I will then present the results of our experimental campaign and conclude the presentation. In recent years, applications of UAVs have gained increasing interest in the literature and industry. Two such applications are delivering packages with UAVs, which could decrease package delivery time substantially, and the human-UAV interaction, where we are seeing increasingly the involvement of UAVs in tasks around humans. In these two applications, the platform is either carrying a valuable cargo or working in close proximity to humans. As such, any failure of the platform could easily inflict property loss or serious injury. Thus, it's very important for platforms in such applications to be robust to the failure of at least one of their propellers. In this context, this paper attempts to first introduce a geometrical tool to understand numerically a platform's ability to statically hover. With this tool, we then analyze the robustness to propeller failure of star-shaped and Y-shaped hexarotors and provide novel observations in the robustness of the star-shaped platform. Then, to prove our hypotheses, we build a novel Y-shaped hexarotor and an equivalent star-shaped platform. We provide open source access to the two designs. We conduct an extensive experimental campaign that shows the robustness of the Y-shaped hexarotor, the partial robustness of the star-shaped, and study the efficiency of both platforms. Let us first define static hovering as the ability of a platform to reach a certain pose with near zero linear and angular velocity. As was proven by Micheletto et al., a platform is capable of static hovering if its moment allocation matrix has rank 3, and at the same time there exists a control input in the set of feasible controls, such that this control input ensures gravity compensation and zero moment. We prove in our paper that geometrically these conditions are equivalent to proving that a platform can achieve static hovering if and only if the origin of the platform's set of feasible moments at hover is an interior point of the set, where this set can be computed numerically as shown here. Let us now focus a bit more on hexarotor designs. A coplanar collinear hexarotor in this work is defined as a platform with 6 identical propellers placed at an equal distance from the platform's center of mass. The 6 propellers all produce thrust along the vertical axis of the platform, while they produce a torque moment due to the produced force multiplied by the arm and a drag moment. Following this definition, we define two hexarotor variants, which are the Y-shaped and the star-shaped. The only difference between the two is the angle between adjacent propellers. The star-shaped has propellers placed equally dispersed around the center of mass, while the Y-shaped has each pair of propellers sharing the same rotation axis. To analyze the hovering ability of the two platforms, we show in this slide the set of feasible moments at hover for each. As you can see, the origin of both sets is an interior point of the set. As such, each of these platforms is capable of static hovering in the healthy case. However, when we analyze the set of feasible moments for the star-shaped platform when it loses one of its propellers, we can see that the origin is a boundary point of the set following the failure of any of its propellers. Moreover, these sets following the failure of opposing propellers intersect only at their boundaries, and as such the origin could not have been but in one of the two. Following this observation, we can conclude that the star-shaped hexarotor cannot compensate for any disturbance moment following the failure of some of its propellers. As such, we can conclude that this platform is not fully robust to propeller failures. On the other hand, we can see that in the case of the Y-shaped Hexarotor, the sets for different propeller failures intersect. Moreover, this intersection contains the origin of these sets. As such, even after the loss of any of the platform's propellers, the platform can statically hover and is thus fully robust to propeller failures. We will now study the effect of model uncertainties on a platform's hovering ability, where we note that each platform has some variance from the nominal model due to manufacturing tolerances. To understand the effect of such uncertainties, let us note that any platform that could not hover after a propeller's loss could eventually hover if we can apply an external moment that shifts the origin of the moment set into the interior of the set. Such external moment could in fact be applied by any external or internal disturbances, for example by model uncertainties. In our paper, we proved that, as we showed before, moment sets of star-shaped platforms following the loss of opposing propellers only intersect at their boundaries. And as such, the intersection between all these sets could at best intersect at a point, and thus has no interior. As such, there isn't a single moment that could be applied to a star-shaped Hexarotor to make it fully robust to the failure of any of its propellers. However, due to the model uncertainties, we expect the star-shaped platform to be able to hover following some of its propellers, but not all, and this is due to the origin shifting into some of the corresponding sets. To study experimentally the robustness of each design, we have built a star-shaped and Y-shaped Hexarotor with identical components and properties. Both platforms are controlled with the INDI controller as a passive fault-tolerant control system. The design of both platforms are provided in the following link as an open source design. We show here the flight of the two open source platforms. As expected, both platforms can hover when all their propellers are functional. The next experiment studies the robustness of each of these two platforms following the systematic failure of each of their propellers. As you can see from this experiment, the Y-shaped Hexarotor was capable of recovering from the failure of any of its propellers, while the star-shaped Hexarotor was capable of recovering following the failure of only half its propellers. Finally, we studied experimentally the flight efficiency of each of the two platforms, where in the case of the Y-shaped platform, the aerodynamic interaction between coaxial propellers reduced the platform's efficiency, while this phenomena is not present for star-shaped platforms. The efficiency was studied by allowing each platform to hover until battery voltage dropped below the 9.8 threshold. We can see that for the Y-shaped platform, this threshold is reached faster than for the star-shaped, and thus the star-shaped is more efficient than the Y-shaped platform. To summarize, in this paper we presented a novel method to analyze the hovering ability of different UAVs. Then we used the presented method to study the robustness of different platforms to propeller failure. To test the presented theory, we built a novel open-source Y-shaped Hexarotor and built an equivalent star-shaped Hexarotor. Finally, we conducted an extensive experimental campaign to compare both the robustness and efficiency of the two platforms. In the future, we aim to build a new platform that could balance between the efficiency of the star-shaped and the robustness of the Y-shaped. The desired design could, for example, vary continuously the angle between adjacent propellers as to optimize the platform design based on the desired performance. Finally, we would like to thank you for watching this presentation and would like to thank our sponsors for their support.